Hello everyone. Suppose we have a pump that draws fluid from a vessel. The pump flow is controlled on the discharge line, and there is a minimum flow controller. So we need to specify the pump for this operation. In order to specify a pump correctly, we need to carry out several calculations. We need to specify its NPSH, we need to determine the pump differential pressure, and hence the differential head, and to calculate its power. Now, after we specified the pump data, we should ensure that the pump is placed in a system that guarantees a smooth pump operation. This would be shown on the pump P and ID. So what are the tips we need to consider for the P and ID drawing of a pump? We need to consider a proper control system to control the pump operation. We should protect the pump from upset conditions that may cause pump damage. In addition, the pump should be maintainable, so we need to isolate it in case of shutdown. The P and ID should provide the means for the operator to easily monitor the pump performance. We shall see each of these tips in detail. We need to consider a proper control system to control the pump operation. The main control scheme is not developed in the P and ID, but it is determined when developing the process flow diagram or the PFD. The P and ID shall reflect this control scheme. Pump control has many different forms. We may also use a variable speed control to reduce the motor speed, hence changing the pump performance curve. Or the most common form can be through controlling the pump capacity. By placing a control valve on pump discharge to control the system resistance. Also, in order to prevent operating the pump at more than minimum flow, we would need to add a minimum flow control. This can have different forms as well. If you want to know more about pump calculations, performance curve and control schemes, you can check out the link in the description. Let's assume that we shall choose this control scheme. But the case is that this control scheme is so simplified, we need to show to our instrument engineer what is exactly required. So we need to show more details instead of this FC. We need to show the flow device that sends a signal to the controller through a cable, which is FC. The square around the circle in the FC here means that its reading is shown to the operator in the control room, and the control valve will be called FE. We also would add tags, so each instrument or valve will have a unique tag to be easily tracked. What if we want to add an alarm to alert the operator that the flow is low? We can add the L letter here. So now this means that there should be an alarm, so that the operator realizes that there is an issue here with the pump flow. We also need to protect the pump from upsets that may cause pump damage. Now, what if the conditions on which we designed the pump were changed to a critical value? For example, this pump draws the fluid from a vessel. We made the NPSH calculation based on the lowest level in the vessel. Let's say it's 300 mm for example. What if the actual level in the vessel dropped to a value below this level? The pump would cavitate. So in this case, we need to protect the pump if the liquid level dropped to 300 mm. This could be done by stopping the pump once the vessel level reaches the upset liquid level or the low liquid level. We also need to warn the operator that the level is dropping and approaching 300 mm. And a signal to the control room to show the operator the current readings of the level. This shall also show the low alarm if the level is 500 mm, and the low alarm at 300 mm. What if, for some reason, a valve on the discharge line is suddenly closed and the line is blocked? This may cause two issues. The first issue is that the pump is susceptible to work at shutoff pressure, which may cause pump damage if it lasted for some time. And the second issue is related to overpressure in the discharge pipe. For a centrifugal pump, this shouldn't be a great issue as the pipe is supposed to withstand the pump shutoff pressure. So if the pump shutoff head is 20 bar for example, then the piping should be fully rated, which means that the piping rating can withstand 20 bar. However, if this pump is reciprocating, this would be an issue. That's why a pressure relief valve is always installed on pump discharge. For the above reasons, it's common to install protection against low pump flow, and sometimes against high pressure in case of using a reciprocating pump. Depending on minimum flow control is not sufficient in many cases. This is because we may need another layer of protection in case the control loop failed. This can be subject to further studies during HAZOP and SIL analyses. There are other protections related to high motor vibration, or current, or other considerations, which are recommended by the pump manufacturer. It's important to note here that if we are controlling the flow using a flow element, and we shall protect the pump from low flow, we shall need another flow element to send the signal to the emergency shutdown system, as these should be two segregated systems to avoid common cause failure of the same flow element, which would paralyze both the control and protection of the pump. This is a general concept that applies to any equipment protection. In addition to the above, we should make sure that no vapor shall enter the pump. One of the causes of this scenario is through pockets in the suction line. You may check out our course related to pipe sizing in the description to understand what pockets are. But here in the P&ID, we will just write on the suction line, do not pocket. The pump should be maintainable, so we need to isolate it in case of shutdown. In order for the pump to be maintainable, it should be isolated from the system. Usually pumps have a spare, so if we need one pump, we install other pump as a spare, so that it shall work while the other is out of service. This means that we won't need to get the system out of service. That's why we always need to isolate the pump we are taking out of service from the system. Isolation philosophy varies depending on the company or project standard, and depending on system design pressure. There are many isolation considerations not just for pumps, but also for different equipment and even for control valves. As this video is related to pumps, we will focus here on some considerations related to pumps. So at each pump, we would need an isolation valve at the suction, and an isolation valve on the discharge. For the operating pump, the valves will be open, but for the spare pump, the valves shall be closed. But still, this won't be enough. A valve may pass fluid to the pump if there is any internal leakage. That's why we need a positive isolation to isolate the pump totally. This would be by installing a spectacle blind on the pump suction and discharge nozzles. By changing the spectacle position to closed, the system would be totally isolated. So for the operating pump, the spectacle blind shall be open position, and for the spare pump, the blind shall be in closed position. Now when we want to operate the running pump, we don't want the fluid to flow back into the spare pump if the valve on the discharge was left open by mistake, or if it is passing fluid, so we shall need to add a check valve at the pump discharge. We also need to make sure when we isolate the pump to dismantle it that the pipe segment has no trapped liquid. That's why we shall need to add drain lines at the lowest point, to make sure there is no trapped liquid in the pump system. So, as we see, we need to make sure of considering different operating scenarios and that it shall be a convenient system, and safe to operate. We should also provide the instruments an operator needs to track the operating parameters. These instruments may be accessible to read in the field only, or to be read from both the field and the DCS, depending on the criticality of the parameter, and the operator's need. Here in case of a pump, we usually add a pressure gauge at the pump suction, and on the pump discharge, which the operator shall depend on during starting the pump. by building up the pressure at the discharge system. This is also applied on the pump strainer at the suction. The job of the strainer is to make sure that no significant solids will enter the pump, especially during startup when the pipes may not be clean. So if the strainer was plugged, this means more pressure drop. During startup, operators need to monitor the pressure drop in the strainer, and when it reaches a certain value, there will be a need to dismantle it and clean it. So we shall need here a pressure differential gauge around the strainer. These are the basic instruments added to monitor the pump performance. There may be a need to other instruments, or to connect these readings to the DCS, to be read from the control room, depending on the type and service of the pump. So as we have seen, there are many guidelines and considerations when developing the P&ID of the pump, whether they are related to control, to pump protection and safety, to isolation, maintainability, and to monitor the pump performance. This video tried to show some of these guidelines. There may be other requirements depending on the pump service, and the current plant situation. Combining all these guidelines in the P&ID drawing is essential in order to make sure we have a safe, operable, and convenient system. If you liked this video, don't forget to press like and subscribe in the channel. If you like to see more detailed courses, you can check out the links in the description. See you in another video.